All right, so with section 2, we look at intermolecular forces. And so we start out this particular section and we talk about what's the difference between intra and intermolecular forces. Now, we've talked pretty extensively about intramolecular forces without calling it intramolecular forces. So intra, if you look at the prefix here, it means within. And so these are forces within atoms, are actual chemical bonds, a covalent bond, a metallic bond even, and an ionic bond. 3 things that we've looked at, okay? Intermolecular forces, again, if we look at the prefix, it's between, okay? So think about this. I gave this example in section 1 notes. If we're in class here and we bump in between one another, we're going to have some type of interaction, right? You have books in your hand, books are going to fall down, things of that nature. Same idea can be applied to our particular molecules, atoms, formula units here, but these are between. And I will also want to point out that these 3 items that we're going to talk about are not chemical bonds. They're interactions between our particular atoms. Even though that one down there says hydrogen bond, that's still not a chemical bond. All right. And then this chart does a pretty good job explaining, hey, what have we talked about before, and what kind of drives that attraction, what drives that either exchange of electrons or sharing of those electrons. Okay. Any questions? Anybody need this? All right. So moving on here, we start with our first of 3 forces. All right, we take a couple slides to actually talk about this, and that's a dispersion force. Okay, first off, every single state of matter, every single atom, every single molecule is going to experience a dispersion force. So yes, there's the formal definitions up here that you're writing down. But what I like to think about this is you have 2 friends take big giant yoga balls and they run at each other. When they run at each other, if we had a slow-mo video, that would show the yoga balls hitting each other, going in towards each other, and then very quickly they bounce off. And if we had that slow-mo video, you would see that yoga ball, because it's a big bouncy ball, would actually elongate and stretch out into this ellipse shape. Very, very quickly, it goes back to normal. Now, during that ellipse shape in a dispersion force, what's happening is you're shifting the positive stuff, the protons, from your negative stuff, your electrons, okay? At that moment, when you get that ellipse shape shown here in that picture, you get a unique distribution of charges. And so very, very temporarily, we get this thing called a dipole, which dipole is a fancy word for positive and negative, or we actually have a pole, positive pole, negative pole on one side. Now, this quickly happens and everything goes back to normal. Just like, again, the yoga ball example, they bounce off each other and all of a sudden the yoga balls are back to their same shape, okay? Temporary, but everything experiences it, right? Questions? Anybody need this? All right, so next thing here is this. Like I said, take a couple slides here. Every single state of matter, because they have protons and because they have electrons, are going to experience our dispersion forces. Because they're temporary and everything goes back to normal, these are the weakest intermolecular forces, okay? So again, because these poles, these positive and negative poles, which by the way, remember that fancy S sign there is just standing for partial positive, partial negative, in this case, partial plus and minus side. It's only temporary, okay? Because it's only temporary, very, very weak, right? You get a little attraction, and I think of this as those little fridge magnets where if you get them close, yeah, they'll start to interact and you'll feel that magnetic pull. But overall, they're pretty weak there, okay? Questions on this? Does anybody need it? All right, so here we go with our second of 3 intermolecular forces that we're going to talk about. Our second force is the dipole-dipole force. Now, again, we just talked about a dipole. A dipole is charged, plus or minus. In a dipole-dipole force or a dipole-dipole interaction, we have to have this key thing under number 2, a polar molecule. Now, if we went back to the chapter on covalent bonds and we talked about, hey, what's polar, what's not polar, we can place that info right here. So a polar molecule, you have to be polar to get a dipole-dipole interaction. The reason for this is that these things down here in the picture, yes, they are partial positives and partial negatives because it happens in a covalent bond, but they're permanent partial positives and permanent partial negatives. Okay, they will sustain that charge. And so again, I like to think about magnets here. We're turning up the strength of the magnet. And so now as you get them closer, you can start to feel more and more of that interaction. And so the interaction in our picture is represented by these dotted lines. Okay, it's not a chemical bond, but think of it as bringing magnets close together. You have your positive, negative charges attracting or repelling each other, depending on if you have mics or opposite charges. Right? You have to, key thing, be polar. Now this is a little stronger than dispersion, just because the poles are permanent. But are there any questions over this? Anybody need it? All right, so our third, and for us, the final intermolecular force that we're going to talk about is a hydrogen bond. Okay, hydrogen bonds. First off, they are the strongest intermolecular force, and I'll explain why. But they are not a chemical bond. Yeah, it says hydrogen bond. They are not a chemical bond. As you can see, the dots between the water molecule here on the picture on the left, it's an interaction between molecules, okay? You have to have some criteria to be a hydrogen bond. 1, you have to have hydrogen. Hopefully that's obvious. 2, you have to be bonded to a fluorine, an oxygen, or nitrogen. Hydrogen has to be directly connected to an F, O, or N. The reason for this is that these things are really, really electronegative. They're going to almost rip away those electrons. They're going to pull the electrons really, really close to it. Okay? Only those 3 atoms bonded to it can form this, and it creates a very strong dipole interaction, and it creates a very strong polar substance. So our strength of our intermolecular force is the greatest right here. Again, greatest is our hydrogen bond. Okay? Questions? Anybody need this? All right. So our last slide here for section 13.2 is this. Hydrogen bonds and really intermolecular forces are a main driving force to explain why there's differences in our particular states of matter. Okay, why does one thing at room temperature act as a gas or is a gas, whereas another thing is a solid? And it all comes back to these intermolecular forces, again, interacting with one another, pushing, pulling, tugging off each other with this. So I know I give a specific example here, methane and ammonia. Ammonia, the reason why it's stronger here, there's actually hydrogen bonds, whereas methane doesn't have it. So if you look at the properties here, the reason that methane is going to have a different boiling point is because of hydrogen bonds and not having hydrogen bonds. Okay. The other thing, ammonia is polar as well, so that drives that. Now, as you're finishing up writing this, just something to think about here. Hopefully in biology you talked about it, or you will talk about it, but real important thing here, ice floats, right? If ice didn't float, our rivers, lakes, streams would actually freeze from the bottom up, and if it froze over, it would kill the aquatic life. Okay, so if the lake freezes right now, at top surface would freeze, it still allow those fish and plant life and things like that to live right there in the bottom. And then when it thaws out in the spring, you get the normal water. Okay, how that happens? Hydrogen bonds. They're very, very strong, and so when they form a solid, they actually expand. So water expands. You've probably seen that. That allows a larger volume, which allows that ice to float. So it's an important process in life. All right, any questions?